Welcome to the Monday seminars. Great to see you all. I suspect that many people know all about this seminar series and what our normal mode of operation is. We're really lucky today to have Men-Andrin Meier with us, who was one of the instigators in the early days of this seminar series, which has grown out of and continues to be supported, let's say, by two ERC projects. Our normal mode of operation is to ask people to mute, do what they want with their camera, interrupt with points of clarification that are short along the way that will help Men-Andrin remember that there are a few of us here, actually, even though he's going to be talking into his screen. But one of the nice things about this format, which worked pretty well, and we'd like to encourage everybody here to take part in, is that the opportunity to have an extended discussion afterward, questions and answers, and extended discussion after the talk. So I'm not going to say too much more. Welcome. Great to see you. Thank you very much, Men-Andrin, for putting together a talk. And please take it away.
Thank you very much, Chris. I'm just trying to see where I can find my laser pointer, Zoom laser pointer. Where's that thing?
Are you in PowerPoint, or are you doing something different?
Well, the Zoom thing has this laser pointer function now.
It's a right click for me. I don't know if it will be the same for you. Right click and opens up some pointer options.
There you go.
There you go.
Very good. Thanks a lot.
Okay, great.
As soon as I get this thing out of the way, I can get started. Okay. Good. Thanks very much for having me. I would like to talk about insights into extensional tectonics from deep learning focal mechanisms. And I also will allow myself to make a comment on some other machine learning tools that I think might be very interesting for this audience. And this is work that I do together with Patricia Martinez Garzón, Federica Lanza, Maria Mesimeri, Nicolai Dahmen, and numerous people have contributed in one way or another with data, comments, etc., including Cristiano, Laura, Maddalena, Georg, and I hope I didn't forget anybody. So as a motivation for this talk, I would like to take the statement of, I think, Greg Barroza and Mustafa Musavi, that machine learning basically offers a new microscope for us to image cross-deformation. Deep learning has substantially improved virtually all tasks of the earthquake monitoring workflow. And so this is an impressive image from the Barroza et al. 2021 paper of the Amatrice sequence, where you have a conventional catalog on the left, where every dot is a little quake, and the deep learning catalog on the right side, where you just have orders of magnitudes of more quakes. And I'm sure you've seen all the interesting studies and the fascinating pictures of how these sort of catalogs can be used to map out, for example, fault topography and a lot of other details that were previously not really clear from seismic data, neither in the waveforms nor in the catalogs. And so the question is, how can we use these new catalogs to better constrain interesting processes, earthquake sequence dynamics, fault zone structure, cross-field stress field? There's a ton of questions that we can ask, and where these new catalogs can help us shed some light on earthquake physics questions. There's also a broader perspective that I would like to make, and that we're basically in the middle of an explosion of methods from the deep learning side, and I'm not sure we're always fully aware of this. Only just a couple of years ago, Andrew Ng has made the statement with the 1 second rule. Andrew Ng is an AI pioneer. He's lecturer at Stanford and founder of Coursera, among many other things. And he estimated, and I think it was in 2019, that if a typical person can do a mental task within less than 1 second of thought, we can probably automate it using AI either now or in the near future. So that was sort of the prospect. And if you've interacted with ChatGPT, I'm sure you realize that this is heavily outdated already. We have algorithms today that can do stuff that is much, much more complex than we can do in 1 second. They can write entire reports, business reports, or applications or whatever. None of which is, of course, perfect, but which is really impressive. And so if you look at these sort of machine learning taxonomies from just a couple of years ago, you see sort of the classic division into supervised learning, unsupervised learning, reinforcement learning. Large language models a couple of years ago were not on most people's horizon, including in Silicon Valley. And so these large language models, they just show the very fast transition that can happen in these new fields. And what is possible today is already very astonishing. And there's really a rapid progress with no end in sight. And most of us is sort of struggling to keep up with these developments. And for example, the model that I'm showing today is basically the state of the art in about 2015. So we're already heavily outdated, but still we're struggling to make use of even those tools. And we just have to ask ourselves, how can we best use these ML tools in science in general? So what I'm going to focus on today is this Amatrice study, where we do use a convolutional neural network to create a large data set of focal mechanisms. I'm going to start with an introduction on the sequence, introduce the method, and then discuss the catalog, and suggest a tectonic interpretation of what we find, and also give a very brief teaser on stress inversion that mostly Patricia is spearheading. This is a whole talk in itself that hopefully we can have at some point in the future. Today, I'd just like to offer a brief teaser. And then I'm going to talk about some other ML tools, in particular signal denoising, and before some conclusions. But so let's get started with the 2016 earthquake sequence. So the 2016 Amatrice sequence was a very intense and consequential earthquake sequence with 2 magnitude 6 quakes, 10 magnitude 5s, and over 1,000 magnitude 3 quakes. In this mostly extensional stress regime in the central Apennines. There have been several hundred casualties overall. And what's scientifically very important and interesting is that it has been recorded by an unusually dense enhanced monitoring network. And you can see here the 3 main shock of the Fausto Amatrice quake, the Viso quake, and the Norcia quake. What's not super obvious on this map is that they all happened on the same fault system of this Vittore fault system, just at different depths. And so on a map, they don't. It's not very obvious from on a map. But if we sort of take this map, just in maybe ugly, so it's the same fault systems here. This is the Sibillini thrust fault. This is the Montevittore fault system and the Norcia fault. And if we look at it from the side, then it becomes a bit more clear. If we now plot the kinematic source model of Tinti et al. For Amatrice, we see now we look sort of into the fault on this right side picture. Then this Amatrice quake had a large number of aftershocks. 3 months later, Viso happens north on the same fault system. Then Viso has its own aftershock, and very shortly after this, the Norcia fault. Now, Norcia, to a large extent, activated the same fault system, but it also seems to have activated this oblique fault to it that is necessary to explain the surface deformation observations. And then there's a very intense aftershock sequence of the Norcia quake itself. And if we rotate this thing a bit from here to here, then we can see the geometry even better. So we have most of the faults in most of the slip of the 3 main shocks occurring on this Montevittore fault system, and then an oblique segment of this that hosted some of the Norcia slip. This sequence has become a bit of a testbed for these new seismicity monitoring methods. There was already an excellent monitoring, just a standard INGV monitoring network above it, and then there was quite a large number of additional temporary stations from the special project, the Central Apennines, under a new microscope. And so this is a sequence that is exceptionally well recorded, and that's why this forms a very interesting testbed. And there are efforts for various numbers of seismicity catalogs going on at the moment. Some of these are published, some of these are in the works. And you see that some of the catalogs they go down to magnitudes of -1 and contain a very large number of events. When I say, I will sometimes refer to CAT4, so the hypercentral catalog number 4, that's a relocated hypercentral catalog by Waldhauser, which has been derived with waveform cross-correlation and the double difference method, and has about 400,000 events, and they reported numerous interesting properties of the spatial distribution of seismicity, including very strongly delineated streaks and boundaries, among many other things. Then catalog 5 is the deep learning hypercenter catalog from Tan et al. 2021. They used PhaseNet detector, which is a convolutional neural network detector. They made 15 million phase detections, and from there derived on the order of 900,000 earthquake hypercenters that were PIC-based relocators with hyper-W. From these studies, there were already a lot of very interesting insights and hypotheses. You can see a cross-section from the Colettini et al. 2022 paper. We see that as opposed to, for example, in L'Aquila, where seismicity is rather concentrated on a very distinct fault plane, we have a lot more distributed seismicity, both at shallow depth, but also at larger depth, where we have this distributed seismicity zone, and of course also, but not exclusively, seismicity on the major fault system. The area is also interesting because there's a lot of additional data from active source measurements. There's geologic outcrops that we think are representative of this area, of some of the faults and surrounding material. And so there have been a lot of interesting insights and suggestions. This is from the Colettini et al. Paper, where they report that there's these, you have the normal fault seismicity, which adheres to this sort of standard expected stick slip behavior, but then there's also distributed seismicity in these Triassic evaporites, where you have a matrix, so to say, that is at these depths ductile, but you still have quakes in these evaporite nodules that are embedded within this matrix, and those two have distinct properties, notably a difference in B values. Here's an interesting insight from the Waldhauser et al. Paper, where they see these bookshelf faults that are off the main fault, where you have distinct concentrations of secondary faults. And now what we're working on, and what I'm going to discuss today, is a deep focal mechanism catalog. I don't know what number it is going to get. It depends on how soon we can finally finalize this catalog. We've been working on it for a long time. What we have done, or what we're doing, is we're starting with this CAT5, so with the deep learning hypercenter catalog with about 900,000 events. And we use that to cut out the waveforms, and then we use a convolutional neural network for assigning first motion polarities. We start with a standard neural network, so most people by now probably know what a neural network is. So I'll be very brief on this. So it's basically a network of neurons at any one where there is very simple operations, where there's just a weighted sum of inputs, then there's a nonlinear activation function, and then these values are passed on to the next neuron in the network. The weights and the biases from every neuron connection and every neuron are free parameters, so you have a large number of free parameters, and so you can make some prediction for an output for some input, and this output prediction is a function of the parameters, the large number of parameters of the network. If we know the true label, for example, if we want to do signal noise discrimination, and if we know if some of the training data is noise or is signal, then we can define some loss function, in this case a mean squared error, just for the sake of the example, where the prediction is this function of the free parameters, and then we can optimize these parameters such that the loss is minimized over a large number of data sets. So we want to find optimal network parameters so that the predictions best agree with the known ground truth. Now, when we work with seismic data, then often it is better to work with convolutional neural networks, because convolutional neural networks, among many other advantages, can work directly with the raw waveform data as inputs rather than features. And so this is a visualization of the convolutional network that we've been using for a long time. So the input are not waveform features, but the actual 3-component waveforms is a segment around the, say, a p-pic. And then the network has a couple of parallel and sequential filter operations. Between these filtering operations, we downsample the time series, and there's activation functions, which are not shown in this visualization. And the end of the last convolutional layers, we just put everything in a large vector, and then we do a standard fully convolutional neural network to come up with 3 numbers. And that's the probability that the input waveform first motion is up, down, or unknown. And so what's special about the convolutional neural network is that this network can learn what it needs to pay attention to pay the task that we train it for. And so the free parameters here in these convolutional layers are actually the filter coefficients. So every one of these filters is represented or uniquely defined by a small number of scalars. Those are the filter coefficients, and those are the parameters that the network learns to optimize. And so we don't have to tell the network or use some expert judgment on what aspects of the waveforms are important for making this prediction of what the first motion polarity is. The network can learn this directly from the data. And so this is a model that we first used in 2018, but we've actually significantly made it smaller, especially the fully connected part here in the end is only 20 neurons per layer. And we trained this model with a very large data set of something like 12 million hand-labeled first motion polarities from the Southern California Seismic Network. We actually used the so-called data to train it, and we just assume that the Southern California Seismic Network analysts, that they know what they're doing, and we take their manual predictions sort of as the ground truth. And if we do that, then we can analyze the classification performance on a test data set that hasn't been used in the training or in the model selection. And then we can look at how often we get the right predictions or how often we get it wrong. If we look at precision, which is sort of the proportional to the inverse false positive rate, so it's the number of true positives divided by the true positive plus false positives, we see that we almost never make false positives, including for very low signal noise ratios. So if we had false positives, then this ratio will go down. But we see that even for very low signal noise ratios close to 1, the network almost never erroneously says this is a up first motion or a down first motion. It would rather say it is unknown. So in that sense, the network acts conservatively. You can do the same thing with recall. Recall is inversely proportional to the false negative rate. So how many of the up cases did we miss to say up? And here you see that we almost never miss any of these individual classes for high signal noise ratios, but then as we go to smaller and smaller signal noise ratio, then sometimes we fail to catch them. And again, this is the consequence of the network being somewhat conservative in that it says, I don't know, rather than saying up or down and then being wrong. We're not using any hand-labeled training data from Amatrice, which is used to Southern California data. And then we apply this Southern California trained model directly to Amatrice as it is. And it turns out that this works really well. How do we know this works really well? If we don't have any labeled training data, but we just look at the very large number of example cases to get a feeling for how reliable these predictions are. And this is something that's very important, that we're, as we develop and rely more and more on these automated methods, that we really investigate the performance of these sort of models. And so here is an example of where we just take the predictions from a network. So this is one seismogram. It has a low signal noise ratio of, in this case, 4.0. We have a probability that prediction for the probability that this is up and a prediction that is down. The network is 33% sure that it is down, although these are not strict probabilities, but it's sort of a measure for the network prediction. And the consequence is that actually this label, the network would say that it is not sure, and this will be classified as unknown. We look at a large number of example cases, and so if we have, for example, a very clear signal, then the network is very confident that this is up. If it's less sure, such as here, it's not quite clear if this wiggle is already signal or if it's down, then the network would say, well, I'm somewhat pulled towards down, but I'm not 100% sure. So again, the classification would be down, unknown. And so by looking at a lot of example cases, we convinced ourselves that the network is actually, when it makes predictions, they're usually reliable, and it's really difficult to find cases where it's clear that the network has a mistake. And so I think that's quite remarkable that a network that's trained in California works really well in Amatrice without any additional retraining or transfer learning. What we then do is, after we've made for all the millions and millions of face detections in the Tanedal catalog, we make first motion polarity predictions with this convolutional neural networks, and then we input those into the Heidelberg-Shearer focal mechanism to compute focal mechanisms. And we're not at the moment, or not yet, using amplitude ratios. And even without using amplitude ratios, just first motion polarities, we get something like 56,000 focal mechanisms. And here's a pretty example of what this can look like. Because we have this unusually dense network in our study area, we get very good coverage of the focal sphere and very clear pattern of polarities. And there's not a lot of wiggle room with which you could get a different focal mechanism. This is a very well-constrained focal mechanism. Of course, I'm showing you a pretty example. One cool thing is that you're not just getting a scalar prediction of up or down, but you actually get some measure of confidence of whether it's up or down. Here's another example from a strike slip quake. And we get 56,000 of those. And we have discussed this before the seminar started. It's actually quite a challenge to analyze these large data sets and really make something of it. It's really can be quite overwhelming. What I want to show in these maps, these are just depth slices of 1 kilometer each. It's just to show that wherever we have quakes, we now also have focal mechanisms. We can look at it, of course, in cross sections, and we see very interesting pattern. We clearly highlight this basal zone of seismicity that is extensively discussed in the Colettini et al. Paper. We also see the larger normal fault events. We have clusters that are very shallow, that are almost vertical, and some rather unusual focal mechanisms. And then there's also clusters where you just have complete misorientation with respect to the expected stress field. So there's a large variety of signals that we can study. And in this talk, I'm just going to discuss some of what I think is most interesting. Here's a magnitude versus time plot of the Cat5, so the deep learning location catalog of Tanedal. It's 900,000 events. And here's the focal mechanisms that we compute. Only about 6% of these events have focal mechanisms, but what we do have is focal mechanisms across the entire magnitude range. I should say not the entire magnitude range, but almost the entire magnitude range, because we actually don't get deep learning focal mechanisms for the largest events. I'll talk about that more in just a minute. I already said that we have 6% of events have focal mechanisms across the entire magnitude range, across the spatial range and the temporal range. And of course, the question is how reliable and accurate are those? One measure for determining the distribution of focal mechanism is to look at what is called the Kagan angle with respect to some reference mechanism. The Kagan angle is the minimum rotation angle between any two focal mechanisms. So how much do you need to rotate one focal mechanism to turn it into another focal mechanism? And this rotation angle notably does not depend on a fault plane selection. It is independent of that. And now what we've taken here as a reference mechanism is the main shock mechanism of the Norcia main shock. So it's sort of the expected mechanism, pure normal fault with a rake of minus 90 on a normal fault that has the expected orientation in the regional stress field, so parallel to the crest of the Apennines. And now we can look at the distribution of Kagan angles. So we compute this Kagan angle with respect to the reference mechanism for every focal mechanism in our data set. And then we can look at what this distribution looks like if we look at the entire data set here in dark blue. So when we use all the 56,000 mechanisms, and so we get sort of this flat distribution with this double peak over here. And then we can look at increasingly better constrained sets of focal mechanisms. So NPU stands for nodal plane uncertainties. So it's the estimated nodal plane uncertainty that the hash method outputs. And so if we look at only the best focal mechanisms with nodal plane uncertainties of less than 10, then we see that we have this very sharp distribution of Kagan angles around something like 20 to 40 degrees. And this is actually also, this is almost identical to the distribution of the regional moment tensors that are from the standard Italian moment tensor catalog as described by Hermann et al. In 2011. So the reference here is from 2011, but the moment tensors that I'm using here are from this same region and from the same time span of the study area. And just for reference, I'm also showing what this distribution would look like for purely random focal mechanisms. And so what we see is that as we go towards from very well-defined focal mechanisms to less well-defined focal mechanisms, we sort of get a broadening of this shape, and we get the secondary peak that to some extent is also present in the moment tensor data, but to a much lesser extent. And so what this means, I think, is that as we include less well-constrained focal mechanisms, we introduce noise from something that originally may have a very sharp distribution, but it gets polluted by observational errors. And so what we're actually doing in the rest of the study, we're only looking at focal mechanisms with nodal plane uncertainties of 25 degrees or less. And so that limits the data set to a still pretty respectable 18,500 focal mechanisms. Now, how about the catalog incompleteness? I already mentioned that 6% of all events in the Tan et al. Location catalog have focal mechanisms. If we exclude all the events with nodal plane uncertainties of less than 25 degrees, then we see that only 2% actually of all events have a focal mechanisms. And you can see this, how this looks as a function of magnitude. So here we plot the number of focal mechanisms in the catalog with respect to the number of events in the Cat5. And so there's this green line, and you see that above magnitude 2.5, we have something like 20 to 30% of the events have a focal mechanism. If we compare to what's in the Waldhauser catalog, then this is more like 30% or to even 40%. But then at where you have the most events down at like magnitude 1, then you get very incomplete. What is important is that this magnitude incompleteness is a very clear function of, or catalog incompleteness is a very clear function of magnitude. And so the higher we go in magnitude, the less incomplete we are. And so if we want to compute a b-value, we have to be really careful. So focal mechanism catalogs are inherently incomplete at all magnitudes, but here we see very clearly that the incompleteness itself is a function of magnitude, and this can create a very clear bias in b-value estimates. So this is something that we should keep in mind. I already mentioned we're missing the large events, and that's because the waveforms are not well represented in the training data set. So we don't have a lot of magnitude 5 and 6 events in any of our training data sets, and their waveforms look very different from the smaller magnitude quakes because the source time function is has a much stronger imprint on the final seismogram than for these very short duration, smaller quakes that dominate the training data set. And this could be accounted for, but we haven't done it. And so this is for now, we just take the moment tensor catalog and we find the intersection with our catalog, and we just add the moment tensor catalog to complement our data set to make it more complete at the higher magnitudes. And then if we do this, then we get fairly complete, of course, at the higher magnitudes. Now let's look maybe at some animations of what this looks like. One interesting way of looking at this, we saw earlier that looking at the map just from above may not be the best perspective because things as a function of depth. And so here we take on a more oblique angle in which we look into the Vittore fault system from above. And so you see here the surface map. This is the Sibillini fault, and this is the surface trace of the Monte Vittore fault system. What's shown here in grayish colors is the finite source slip models of the main shocks, and where the labels are a bit small, but so we're going down from depth. So now we're just at the top layer, and now we're going to go to increasingly larger depth. The color of each dot of each quake is proportional to the rake. So red colors suggest a normal faulting mechanism, and blue colors suggest thrust mechanisms. And one interesting observation that we already make is that we have very shallow thrust events that actually locate on some of the surface mapped normal faults, like this case here. If we go further down, we have more of these mechanisms, including some larger ones. And we also see very clear concentrations of seismicity clusters around the edges of these fault zone models. Another interesting feature is that you see here, even these thrust faults show pretty clear correlations with seismicity at depth. And this is actually also true for the Sibillini thrust itself. I'm not sure if this extrapolation is valid, and maybe some of my tectonic colleagues are not going to be pleased to hear that, but there is a striking correlation of some of these events with the surface mapped Sibillini thrust fault if you look from this particular angle. If you look here on the other side, can you still see my cursor, Chris? Thank you. You see that we also have clusters that have the right orientations, but they're not red at all, meaning that they're including now, by now we're at 3.5 kilometers depth. We see very distinctly different mechanisms, even though they line up on faults that have the perfect orientation for a normal fault in that area. And so as we go deeper, we also see some of these bookshelf faults that Waldhauser and colleagues refer to, pretty clear lineaments that are parallel to each other northwest of the main shock fault zones. And then as we go deeper, below 7 kilometers, we start going into this basal seismicity that is no longer on these normal thrust faults, but that forms this basal zone of distributed seismicity. In some areas, such as to the west of the main shocks, this is pretty distinctly normal seismicity, but in the footwall, actually, there's a lot more diversity and a different sort of mechanism, which is something that we'll see later on again as well. So you see here that there is more variability here in the footwall than in the hanging wall. Okay, and now I would like to go a bit further in this, in sort of how to make sense of what we see. One striking pattern that we see is that we have a very clear depth dependence of these focal mechanisms. Here I show, again, the Kagan angle with respect to the reference mechanism of Norcia as a function of depth. And so every one of the 18,000 focal mechanisms in our data set is a dot on this plot with the symbol size somewhat proportional to rupture size. Again, the Kagan angle is the minimum rotation angle with respect to this mechanism, and the color of each dot is given by the same color scale, with red for normal mechanism and blue for thrust events. And strike slip events are sort of in grayish colors in between. And what we see immediately is that somewhere between 2 and 9 kilometers, we have a very strong dominance of the expected normal fault mechanism with red colors and low Kagan angles. But then strikingly, as we go above 1.5 kilometers, then these type of mechanisms almost completely switch off. And instead, we have a lot of strike slip mechanisms and even thrust mechanisms. And these are the ones that we saw earlier when we looked into from an oblique perspective. Likewise, if we go deeper than 9 kilometers, then we see also that we have much fewer normal faulting mechanism now, and then we go much more, not towards thrust down here, but towards strike slip mechanisms. And the dark gray lines that you see, these are actually percentiles, the 16th, the 50th, and the 84th percentile in slices of depth. And so you see how you have this distribution change here at about 1, 2, 3 kilometers towards away from the normal mechanisms, and down here after 9 kilometers you go towards mechanism. Maybe if you look closely, you see these gray lines down here that I use as sort of help lines. These would be the percentile values if the mechanisms were perfectly random. And we see that we're not quite there, so we don't have perfectly random mechanisms, but we just have a much larger variability of mechanisms. What we can also look at in the same depth profile is just the number of events of seismicity. So the number of quakes in the Waldhauser catalog in pink, and in dark green for the Tanedal deep learning catalog, we see that seismicity grows over the first 2 or so kilometers, and then it reaches some stable value and then another peak at some depth. The same peak is also present in the Waldhauser catalog, but much less prominently. And then we can...
Yeah, it's Chris. Yeah, sorry to interrupt, but I didn't follow you. Those 3 lines on the left, you said they're for random. Why are there 3 lines?
The vertical ones. This is for comparing with the percentile. So there's there's help lines in vertical and in horizontal. The horizontal here that you see here are just to show the same depth. The vertical ones are the 60th, 50th, and 84th percentile of the Kagan angle for a uniformly random fault mechanism.
Gotcha. Thanks. Yeah.
And the third plot now that I'm showing over the same section is the fraction of cumulative seismic moment for the 3 different faulting styles. So dark red for normal mechanisms, gray for strike slip mechanisms, and blue for thrust mechanisms. And now we see very clearly that in the first 2.5 kilometers, we have a dominance actually of strike slip mechanisms, and then it suddenly switches to a strong dominance of normal mechanisms, and then deeper than 9 kilometers, this dominance starts decaying, and then it just becomes much more versatile and more towards strike slip mechanisms again. How can we make sense of this? So, of course, after sort of the classic rate and state interpretation, we expect seismicity to be limited to the depth range with frictionally unstable fault properties. So we expect that even though the fault strength might be strong enough to store elastic strain energy, at some point we no longer have unstable rupture and nucleation conditions. And this is true both at shallow depth, where we have a lot of unconsolidated maybe granular material, and also at large depth where we can have ductile flow. The other thing that we expect for the depth dependence is that the vertical stresses may only become large enough at a certain threshold depth. So this is an old paper from Cooling 1988 that shows this. I actually am not aware of very good more recent references. I'd be very interested in comments, but they show that basically vertical stresses from the overburden, of course, they go to 0 towards the depth, but the horizontal stresses, depending on the stress regime, can be higher even at very shallow depths. And so there's a crossover depth at which the vertical stresses become dominant, and therefore we would expect normal faulting mechanisms only after a certain threshold depth. And so if we think of this perspective again, where we see that seismicity ramps up to some threshold depth and then starts decaying below a certain threshold depth, and we have another depth at which the dominance of normal faulting mechanism comes in, we can think of it as sort of a complementary picture where we think of fault stability. So this is the top 1.5 kilometers, maybe the region where we have little seismicity because we do not have unstable frictional conditions. And then at larger depth, the same holds true. And the unstable regime would be the one where we have by a large margin the largest amount of cumulative seismic moment. And then we can also think of what we need in terms of the strength of normal fault. And one possible explanation for this change here between strike slip and normal mechanism is that above this threshold depth of here about 2.5 kilometers, the normal faults simply don't have enough overburden to be mechanically strong, so that the compressive stresses on these normal faults are not strong enough so that these faults cannot store substantial or sufficient amounts of elastic strain energy that would later be released in quakes. And so we have these two different depth thresholds that do not necessarily, from the nucleation conditions and from the strength of the normal faults, and they don't necessarily have to be at the same depth. And so we have basically 4 regimes: the shallow regime D1, where we have little seismicity, generally little seismicity, and there's D2 where we already have a lot of seismicity, but it's not yet normal. And then there's the main regime D3, where we have all the strong dominance of normal mechanism and most of the seismic moment, and then D4, where ductile processes can play a role and lead to yet another change in seismicity. And so in this interpretation, this segment between 2.5 and 9 kilometers is really what holds the crust together, that these normal faults at this in this depth range is what prevents the crust from spreading farther. Interestingly, we can also bring in magnitude frequency distributions into this, and this is a bit preliminary, but I think it's still very interesting. So these 3 lines here show the 50th and 95th percentile of the magnitude frequency distribution, and then the last line is the maximum magnitude at each different depth for the 2 catalogs. So for catalog 5, the deep learning catalog, and for catalog 4, the Waldhauser catalog. And it's really striking how little this distribution changes with depth. We can of course compute B value, and that's the preliminary part. I meant to implement B positive before this talk, but I haven't managed, so this remains to be checked. But depending on which catalog you look at, so if you look at the deep learning catalog, then there's no B value change whatsoever, including at very small depth. The Waldhauser catalog actually then would show a strong excursion for the shallow events. But so apart from this very shallow depth, it seems that, well, and if you if you believe this preliminary result, is basically suggests that doesn't matter where an event nucleates, or once an event nucleates, so the likelihood of it becoming large is pretty much the same everywhere, except maybe in this top kilometer. And there's not really a clear signal that you're more likely to grow big if you nucleate at larger depths, which I think is surprising. Another thing that we do with the focal mechanism catalog is stress inversion, and this is mostly the work of Patricia, who I think is in the audience and can correct me if I say something wrong. Again, we use all focal mechanisms with nodal plane uncertainties less than 25 degrees. We use a iterative k-means clustering to make pockets of seismicity that we can then use for the estimating stresses. We take every cluster at least needs to have 40 events, And then we perform an iterative linear stress tensor inversion with the Mzatsi method of Patricia and colleagues, and the stress inverse method of Ravlichuk. And then we can study how different stress parameters vary in space and time. For example, how the maximum horizontal stress varies in time, or the stress ratio R, or the A-phi Anderson parameter. And we find some really interesting temporal trends, particularly after the Viso and Norcia main shock. So here's how SH max changes in the top 4 kilometers as a function of time. And you see that here something changes where this variability seems to be reduced quite significantly, although the overall amplitude is not so strongly changed. If we go to deeper depths between 4 and 6.5 kilometers, now it's again SH max, just a bit deeper. You see a very significant trend of probably at least 10, if not 20 degrees of this SH max just shortly after Norcia. If we go even deeper, then this signal in SH max is again not as clear, although again we have this maybe less variability. I'm not quite sure to what extent this is a real trend. The strongest trend that is quite striking, I think, is at large depths for the A-phi Anderson parameter that gives you the sort of the proxy for the faulting regime, where you go from 0.5 almost down to 0.3, and then you recover over the time period of a couple of months back to the initial levels until the Campotosto event, and then you have yet another jump until you go back to maybe a background level. And so as a summary for these observations, so we have compiled a fully automated procedure for computing 18,000 high-quality focal mechanisms. We're still performing tests on to see which ones of these results are reliable. As a somewhat cautious tectonic interpretation, I think we see rather distinct depth-depending faulting patterns that show us over what depth range the crust is mechanically strong. So it's these 2 to 9 kilometers where we see all the normal faulting that I think essentially hold the crust together. And as I just showed, we also show some, the focal mechanisms also reveal some main shock-induced transient changes in the stress field. And with this, I would like to transition to a slightly different topic that may seem a little bit out of topic, but I would like to show it in this community because I think it may be a little bit underappreciated. And that's actually a signal denoising tool that Nico Dahmen has developed in the here at ETH in the context of his PhD thesis, which he just very recently defended successfully. So I guess now it's Dr. Nico Dahmen. Nico was analyzing the InSight data from the NASA mission InSight in when a couple of years ago NASA placed a very sensitive seismometer on the surface of the moon, Mars, excuse me, and this resulted in about 2 full Martian years of very high sensitivity seismic data. As you see in this, the spectrograms in this animation that has very interesting noise characteristics with seasonal variations, daily variations, especially when the sun is up, there's very strong wind-induced noise. In general, because there's no oceans and therefore no ocean noise, in these Mars recordings, you can detect much, much weaker events, smaller events at larger distances than would be possible here on Earth. What Nico developed is a deep learning signal denoising method based on a fully convolutional neural network. This is a so-called UNet that was first introduced by Ronneberger et al. And then adapted to seismic problems by Su et al. From the Stanford group. The way the method works is that you have some noisy input signal, a 3-component signal, You compute spectrograms with imaginary and real parts for the 3 components each. And then you train a fully connected neural network to predict what are called segmentation masks. And the segmentation mask is for each of these input spectrograms a matrix with values between 0 and 1 that would separate the noise from the signal. And so if any of these values is close to 1 and very dark, then it means that a particular frequency time component would be considered noise. And if it's close to 1 in the signal or event mask, then that would be the prediction that this is part of the signal. And once you've predicted this segmentation mask for some input seismogram, then you can just multiply the spectrogram with the segmentation mask, and then you get separated representations of the noise and the event or the signal. And then all you have to do is compute an inverse short-term Fourier transform to go from the spectrogram to the time domain series, and then you have a noise waveform and a waveform that is denoised. And this has been trained mostly with synthetic data because there's only been a small number of very well recorded events from Mars. And so we don't have a whole lot of training data, but despite this has worked quite well in that we find something like 60% more events than the standard catalog. So these are all the detections in orange from the Marsquake service, which is a very careful manual operation. So there was the Marsquake service that would revise every day the data by hand and make a manual seismicity catalog. And this Marsquake net, as we call it, this denoising and detection method redetects virtually all of these events, but then on top of that adds 60% more of the quakes. And then I think we're sort of naturally and healthily skeptical with respect to such methods that are fairly complicated and maybe to some extent also black boxes. And so you can ask the question, to what extent does this denoising signal distort the actual signal? And the result is quite fascinating, I find, which is why I really wanted to show it here. And we can actually find this out by taking some of the best recorded signals. So this is a real signal from Mars, and then we just add noise, and with increasing noise amplitude such that we really degrade the signal noise ratio. And then we can compute the cross correlation of the resulting noisy signal with the original undisturbed signal. And so if we do this, at some point, we would just be autocorrelating the signal with itself. So you get a cross correlation of 1, and then as you degrade the signal and add more noise, this cross correlation coefficient goes down and eventually to 0. Now, a typical method that we would use for getting rid of some of the noise would just be a Butterworth bandpass filter. And then you see how you can maintain a high cross correlation between the noisy signal and the original signal, even down to much lower signal noise ratio. So you can essentially denoise the signal with a bandpass filter, but then of course it also at some point degrades. Now, what I think is really spectacular is that if you do the same thing with this denoiser, you see that the denoiser actually performs substantially better than a commonly used Butterworth filter at all but the lowest noise levels. So this deep denoising strategy actually distorts the input seismograms less than Butterworth filters like we all used to do. And I think that's quite unexpected and quite spectacular. So in summary, Marsquake net has been used to denoise inside seismic data with a deep convolutional neural network, and it was trained entirely on synthetic data. It increased the seismicity catalog of a carefully crafted manual seismicity catalog by over 60%. and this is documented in Nicodemus, one of Nicodemus' papers in JGR Planet. And I think it's maybe not a paper that many of us have on the radar because a lot of us only work on Earth. Notably, this deep learning denoises distorts signals less than a commonly used Butterworth filter. And with this, I would like to transition back to Earth and wrap up with some overall conclusions. I think in general, these machine learning methods, like these denoisers and signal classifiers, allow us to make much more of our raw data. These better data products facilitate insights into cross-deformation processes like the strength profile of the extensional crust that I've been trying to show. I think there's an explosion of methods with no end in sight. The large language models that we briefly talked about initially, they've only just became a thing. The underlying model of ChatGPT, at least GPT-3, is already completely outdated and is considered by a lot of domain experts in data science as actually a rather poor model. And it's just really fascinating, to some extent also scary to think what the models, the good models at the moment, but especially also the models maybe 5 years from now, can potentially do. And I would like to stop with a word of caution, maybe, that we really need to carefully investigate the results of such automated procedures. This is both necessary and challenging. In our particular study, we're still investigating at various ends, not just if the focal mechanisms are reliable, we also need to ask ourselves how reliable are the input locations from the Tanadal catalog. There are, in any of such automated large-scale catalogs, there's definitely things that are maybe not accurate, and we have not yet developed general tools with which we could find this out. So this is an important line of work for the months and years to come. Thank you very much for your attention.
Beautiful talk, Men-Andrin. Thank you very much. I'll invite people to join me thanking Men-Andrin. And as we're getting ourselves organized for questions and discussion, and Men-Andrin has a chance to collect his thoughts for a second, I will invite all the people who are watching this later on YouTube to join us. If you found us on YouTube, then you can find a way to automatically become part of the weekly announcements about the seminar series. And yeah, there's something that's useful about for everybody, but including Men-Andrin. Of course, the speaker is something useful about having people actively involved in discussing and asking questions and keeping track. So we end up with a number between 75 and 100 people every week, and please join us. Right now, I'd like to invite people to use the reaction button at the bottom of their screen and raise their hand. It looks like this. And thank you, Bill Ellsworth already did. So we'll go to Bill, and at the same time, really encourage people to join in, right? So especially early career people, this is an easy opportunity to get involved in the discussion, to ask your questions, to have your voice heard, and to have people know who you are. Bill Ellsworth, please go ahead. Bill, you're still muted. Lower left of your screen is a mute button, Bill. So Dave Shelley, do you want to go ahead, and then we'll grab Bill as soon as he comes back?
Sure. Yeah. Thanks. That was super cool. It's really exciting to see the potential to, start to analyze focal mechanisms for these huge catalogs. I wanted to ask about, one of the things you talked about early in the talk, which was, that essentially you're labeling a large percentage of the machine learning determinations as unknown. What's the rationale for that, rather than just relying on these kind of confidence? You had a certain percentage P wave, certain percentage S wave. Why not use that data or use that information rather than just saying it's unknown?
I'm not 100% sure I understand the question. So that why don't we use the certainty level that comes out of the neural network?
Yeah, because you showed some examples where, there was a, 3 times as likely to be an up rather than a down, but you still labeled it as unknown and essentially, throw out that information. Why not just keep those, um, keep
The
those
probabilities.
probabilities as weights in like the focal mechanism inversion?
Yes, I think this is definitely something that we're thinking about. It is a bit more complicated than that because the output of the neural network, they're not probabilities, they're uncalibrated, and they very strongly just depend on the activation that you use in your last layer, and you can either like squish these or extend them. But there are methods now to calibrate such classifiers and regressors. And um and so this can be done, and then you can use it as to basically compute a probabilistic fault mechanism. It's just that this is a bit more work and we haven't done it yet.
Cool, thanks. Yeah, I guess one other note is I think Rob Skumal has an updated extended version of hash called SK hash that is already set up to use weights in the measurements for polarity, so you don't have to just give it a classified up or down. So in case that's useful at some point.
I didn't know that, and that is very interesting and useful. Thanks.
Cristiano, I think Bill Ellsworth is back. He's got his,
Can you hear me now?
yeah, go ahead, Bill, then we'll go to
Great.
Chris.
Yeah, so really super interesting stuff, man. I had kind of one machine learning question and then a tectonic question. The machine learning question concerns the amplitudes. I think you're absolutely right that that's a dangerous place to go blindly. But have you thought about using these data set to actually train the amplitudes? As we all know, if you go to a nodal point, the shear wave is not going to be zero amplitude. The P wave's not going to be zero at the node. Maybe there's a way of engineering things so we can actually begin to use the amplitudes, which have been challenging.
What do you mean with training the amplitudes?
So you have focal mechanisms that are determined now. And if you were to measure say the amplitudes and use those as those are the variables you want to predict. Using the known mechanisms now as the training data, basically. I think there's an opportunity for someone there to really move things forward in this direction.
So can basically predict amplitude residuals, you mean?
Well, to train a network to use the amplitudes, to understand better about what they're actually going to be able to tell us. I mean, that's something we often have, even when we can't read a polarity reliably, and it allows us to use shear wave information that is abundant, but is difficult to use otherwise.
Mm-hmm.
Anyway, just a suggestion. So my tectonic question concerns the variability in the A phi values. Are those being dominated by the immediate aftershocks in a small region around the main event, or do you actually see changes throughout the entire zone? So for example, following Viso and Norcia, do you see changes in the Amatricia zone, or are they really just localized and the numbers go up simply because of the number of seismicity that you're getting?
Yeah, I think they're localized to the extent that seismicity is localized. So in the direct aftermath of Norcia, there is a lot of seismicity directly around these the main shock patches, but then it's actually one of the observations that are documented in the Coletini and other papers, that there is widespread triggering in a rather large volume, including away from the main shock patches. And so how strongly it's dominated by local effects is, I guess, something that will be a bit more complicated to evaluate. Do you have a particular effect in mind when you ask that?
For example, if you look at the Viso event, it's almost like a fairy ring where you have this circle of seismicity aftershocks that surround it. What do those mechanisms represent? Do they represent more normal faulting, or are they showing, some more complexity? I think those are some interesting things that would be worth examining in greater detail. I'm sure you will.
Yeah, good suggestion. Thanks. Those are indeed the Viso aftershocks, very interesting.
Great.
Thanks, Bill.
With Cristiano, I'll re-invite people to raise your hand, join the discussion. Cristiano.
Ciao, man. Thanks a lot. Very, very interesting talk and very extensive data set. And yeah, of course, when you have got just a few focal mechanisms, the interpretation is super easy. The three main extensional focal mechanisms consistent with the regional stress field. When you have got more than 50K focal mechanisms to deal with, the interpretation is more complicated, but this is the beauty of the complexities we can pick up in nature. So yeah, that said, I have got one comment I would like to do for the compressional and strike slip focal mechanisms. You have very well documented at shallow crustal levels. And if I well understand, you are suggesting a sort of absence of an extensional stress field at shallow crustal level. You need to reach 3 kilometers of depth in order to have this extensional stress field. And I do not agree too much with that. And yeah, because, for example, the landscape of the Apennine is strongly influenced by extensional tectonics. So you have got these flat intramountain basins that are bordered by normal faults that, of course, to influence the landscape, they reach very shallow crustal levels. They reach the surface. And then second, if you go in the field and you look at small displacement normal faults, not only the large normal faults that bound the intramountain basins, but the small normal faults, they are present up to shallow crustal levels, and they are in some way consistent with the regional stress field. So I was wondering if maybe some stress changes, some stress perturbations induced by the main shock can influence the stress field at shallow crustal level. And in support of that, I was thinking about the Tohoku aftershocks. For example, at very shallow crustal level, most of the aftershock of the Tohoku, they have got extensional focal mechanisms. And yeah, I think that everyone agrees that in Tohoku, we are in a compressional environment along a subduction zone, but the total stress changes, this is an interpretation produced by the main shock, allow this stress release at shallow crustal level, and so the switch in an extension. So yeah, I was wondering if this well-documented compressional and strike slip focal mechanism at shallow crustal level can be the result of some stress changes induced by the main shocks.
Thanks a lot for both comments. At the first one with the landscape, I mean, I'm not a tectonics expert, but couldn't you also have the surface expression if you only had normal slip at depth, so that you would still have the same surface expressions, even though at shallow depths you may not have the same co-seismic rupture mechanisms, or if these would actually be aseismic rather than seismic? And the second point is, I think that's absolutely true. So here we get a snapshot of 1 year around the main shocks, and so you may very well have other mechanisms at other times. It's just that we don't sample them. And I think it's a very plausible explanation for these reversed mechanisms, that, as in the Tohoku case, you may have complete stress drop and then an actual reversal of slip, just because, yeah, it's just main shock induced reversal from the stress changes. Now, Massimo's going to be the most difficult one. Massimo asked me before the seminar if these machine learning tools are any use for anything. And so now it's the moment of truth. Massimo, did you find this remotely convincing?
Go ahead, Matt.
Any of it?
Yeah, actually, I have one question that is related exactly to that, and two comments which are related to the Bill's and Cristiano's question. But my question is the following. So if you have this marvelous and huge catalog of full plane solution, are you enabled to perform a careful spatial-temporal analysis? Because the statistics is important, But I think that the only way to properly answer to the Bill's and Cristiano's questions is to analyze in space and time how these focal mechanisms are distributed. Because this is important essentially for two reasons. First, because in the fault segment between Amatrice and Norcia, we have a surface expression, which is perfectly normal, and the fault slipped twice during the Amatrice earthquake and during the Norcia earthquake. So why that fault segment was loaded in a way that slipped twice at depth and at the surface? And therefore the question is, can you perform a careful spatiotemporal analysis? Because if the results are simply too complex, that inhibits a careful spatiotemporal analysis, therefore we have a question. Or our analysis is too simple for the real complexity of the Earth, or perhaps we should be able to extract the most important signatures for all these data.
Yeah, thanks, Massimo. So we are, of course, working on a careful analysis of the spatial temporal evolution, and it is a challenge because of with these huge data sets, we do have a lot of noise in them. I try to show sort of the uncertainties in the focal mechanisms and to what extent. So we have the true distribution of the true unknown distribution of focal mechanisms, and then the observed perturbed distribution of focal mechanisms. And so seeing the patterns through in this real and data that is quite strongly perturbed by observational errors is a challenge. It's also, I think, more difficult because of the geometry of the thing. So in California, where many things are strike slip, you can just look at maps and things are easier. And here it's just the geometry itself is a bit more complicated. The fact that the fault slipped twice, I think, is a argument for dynamically weak faults, so that the faults are only weak during the rupture, which is how it can be possible that Amatrice ruptures a large extent, and then adjacent segments do not get it immediately triggered, and only later they can actually rupture in a second event. So it's a rather
but it is also
fickle
important
and unstable event. How this would reflect in a focal mechanism distribution is not super clear to me, although it's of course interesting. But what we've tried to focus on here is sort of the very first order broad patterns, which is, I think, this overall depth dependence. Of course, this is also, different in different regions. There's a temporal evolution to all of this, but still we observe this relatively, I think, distinct pattern with depth. And so this is, I think, among the most stable results. Sorry to interrupt you.
No, what I would like to say, because for instance, if most of these shell of strike slip earthquakes are on the footwall of the normal faults and along the reactivated thrust faults at shallow depth, to me, the easiest explanation is, as Cristiano said, is stress change caused by the normal fault earthquakes, by the Visso and by the Norcia earthquakes. And I would, it's difficult for the way in which we study so far the normal faulting in the Apennines to interpret this in terms of weakness of the crust, because I fully agree with Cristiano. Therefore, to me, it is extremely important that with this type of catalogs, we are able to do a spatiotemporal analysis, also to see, as Bill said, if, for instance, the focal mechanism change, for instance, after Visso on the Norcia, or after Visso and Norcia on Amatrice. In particular, because in any case, in this sequence, we should always remind that the Meier shock occurred at the end of the sequence. Though it must be stress interactions, because this is completely counterintuitive. The 6.5 is the last of the Meier shocks.
Yeah, fully agree. And of course, this is, not the end of the story, but only more the beginning. and there's these sort of the stress interaction quantifications that I think you suggest should absolutely be done, and hopefully will be very interesting.
Great points, Massimo. Thanks very much. Patricia, go ahead.
Hello. Thanks a lot, and thank you, Men-Andrin, for a great talk. I wanted to give some comments from the stress inversion point of view on some of the questions that have been posed over the last round. First one regarding the question by Cristiano on the shallow part, whether there is a change. So I think we do see a change from preliminary results, let's say. There seemed to be some transition from strike slip or oblique towards more normal faulting. And this is particularly more evident on the very shallow part, so from 1 to 4 kilometers depth, and also at depth larger than 6.57 kilometers. And also regarding the question by Bill, which I'm not entirely sure if he's here now, but just in case, he mentioned about the distance at which the stress change from the main shock could be observed. And we started to make some effort to quantify the deviation of the stress field orientation from a reference value with the data that Men-Andrin shown, of course. And we tend to see that the largest stress deviations from the reference occur up to 5 to 7 kilometers away from the main rupture planes that were activated in the both Amatrice and Norcia. That's it. Thank you.
Yeah, I forgot to mention this. Thanks for the addition, Patricia. We do actually have some estimate of this, like Patricia just explained.
Yeah.
Great point. Georg, go ahead.
Yeah, Men-Andrin, very nice talk. Now, short question with regard to the reverse mechanisms also. These shallow events, do they systematically occur? I may have missed that. Do they systematically occur on the footwall side or on the hanging wall side of the Monte Vittore? Do you know that?
It's hard to say if they're on the. Let me try and find a figure which may be a little bit outdated, but still instructive. I think I had it somewhere. Just 1 minute, please. There you go. This is a bit of an outdated plot, but so this is a map of all the events in the top 4 kilometers, and you see the red faults are the mapped thrust faults, and the gray ones are the normal faults. And again, it's the same color pattern as before. If we take out the events with a negative rake, so if we only plot the ones with positive rake, then you see that these actually correlate rather well with the mapped normal faults. So these are thrust events that correlate quite well with the normal faults. And especially they seem to correlate a bit with complexities in the mapped normal faults, that where these mapped faults show junctions and convergence, you seem to have more of those. So I think there could be also a consequence to some extent of fault network complexity. Whether or not they're in the hanging wall and the footwall is a bit hard to say, because you have to extrapolate some fault plane, and then I'm not sure we have the resolution for that. Do you have some model in mind when you think about that?
No, there was just
expect them to
curiosity.
be okay.
No.
But Men-Andrin, for instance, if I can, here it seems to me, I'm not completely sure if I am interpreting well the position of this map, but it seems to me that most of the reverse of the thrust, the compressional events, are in the area where one of the model by Tinti et al. Proposed that the normal faults during the dynamic rupture of the main shock of Norcia reactivated the thrust ramp. which would be exactly where are these cluster here, because yeah, looking at the hypocenter, it seems that would be that. So if this is one of the possibility, I know that there are many other models that disagree with that. But what I can say for what we studied for that model was the only one that was able to explain the directivity of the strong motion data. And many of the other models did not fit the strong motion data, but just the geodetic data, GPS, high frequency GPS or SAR data. So I think that the presence of this thrust fault could be explained by the complexity of the main shock, which reactivated that. But it's surprising that exactly I got the wrong impression before that most of the strike slip could be on the footwall.
And these, so what are these reactivated thrust ramps that you say? So these were surface deformation
It is more or
observations?
less, if I am well interpreting, you see where you have this cluster of thrust faults, this one exactly, from there going perpendicular to the normal fault. I think that, I don't know, perhaps Cristiano.
This is the normal faults. The
Yeah,
thrust faults
exactly.
are in red.
From
But
this
this
cluster,
is the
that
Montevideo.
yeah, for the where you are now, go perpendicular to the normal faults. Yeah, this direction. I think that the ramp should be located there.
Interesting.
Yes, the ramp is exactly the thrust in red in the surface shallow map, but because the dip is very low, you reach at the end the hypocenter of Norcham.
And also there is another interesting things, which of course it is not for this discussion on the Amatrice, because the Amatrice earthquake, the August 24, which is the southern star here, actually it ruptured two segments of the fault, which belongs to two completely different geological regimes, settings. So there are geologists that believe that this earthquake actually is a double event. From seismological point of view, this is impossible because we have one nucleation. But it nucleates in the less probable place that we would expect before, because it subtly nucleates at the beginning. And for what we saw, the propagation toward Norcia and the propagation toward Matrice during the main shock was quite different in terms of kinematics. And for instance, we have no aftershock on the Amatrice side, on the southern part. So it is a complex settings for sure. And to me, the stress interaction with this complexity should dominate the rotation of the stress.
Bunch of interesting stuff. Men-Andrin, I raised my hand to say thank you personally for a fabulous talk. I also want to,
Thank you.
we have a few more minutes. I want to encourage everyone, especially young early career people, to join the discussion if they have a question. And I will, in the meantime, ask one of my own, because various people have asked interesting questions about the time dependence of things. And you showed us some plots of the rake directions, I think, in the stress directions as a function of time. But did you also plot rake as a function of time, or focal, try to like understand if there were differences in dominant focal mechanisms before and after anything? Man.
I did analyze this quite extensively, and just by looking at individual focal mechanisms, but Tricia may not agree with my statement, I didn't see very obvious first order trends. I think the advantage from looking at it through the lens of stress inversion is that you get a sort of a smoothed picture of that. You know, the stress inversion smoothes out the contribution of all the individual focal mechanisms. And then you see these very clear trends, like, for example, with the A5 parameter.
Right.
Maybe I just looked in the wrong way, but when I just looked at, for example, rake versus time in certain areas, then there is not a super clear trend.
Yeah, okay. But there's an interesting trend after Norcha that you know could indicate some kind of a healing mechanism, I suppose. Yeah. Georg, did you have another question? I know you still had your hand up. Sorry, you're muted, Georg.
I missed to put it down. Sorry.
Yeah, okay, it's fine. No, we're still, yeah. Someone else has something? All right, well, okay, we're perfectly on time, and Men-Andrin, I'm sure, has more things he has to take care of this evening, so please join me in thanking Men-Andrin for a fabulous talk, really great talk. Thank you very much.
Thank you very much.
Great to see you all.